So let's actually start with prayer, and then we'll get to it. God, we thank you for today, for your care for us, for the opportunities that we have today. We pray for our seniors that you will help them have a great time with their picnic and keep them safe. And we ask for your blessing on our class, that it would be clarified. Amen. Okay, so Austin comes in, and Amanda right after him, and said, I had these homework questions. What do I do? And the answer is, post your questions on Edmodo because somebody else may well have your questions. See, Amanda and you had questions, and they were the same exact questions, and who knew? Somebody could have come along like Grant and said, well, all you got to do is divide by the page number, and you go. So, we will actually take a look at 2 homework questions of your choice, and then we're going to get right to density. Okay, go ahead.
On 43.
Uh-huh.
So I put how, so I put it in a conversion factor, and then I put 1 ton, 2,000 over 1 ton times 1.
Okay. First of all, what was let's get your wild guess first. What was your wild guess? How big is a ton?
A ton in the rock density of the rock, right?
Yeah.
I guess 3 feet.
3 feet. Okay.
Because every day you need 3 feet.
Okay.
The size of a car is so big.
I like that guess.
Okay. I didn't know how to put that in. Get the answer out in it with conversion.
Okay, so your guess is a 3-foot cube.
Yes.
So 3 by 3 by 3. Great. All right. Now, tell us your computations that you have so far.
So. I have a 1 ton rock.
Uh-huh.
That's times 2,000 pounds over 1 ton.
Mm-hmm.
And then I have times 1 foot cubed equals 62 pounds.
Did they tell us that, or did you find it?
Well, yeah, they tell us that. Cause then I was trying to get the volume of the water, and then I would.
Okay. So this is water.
Yeah.
Okay, great. So water is going to be less dense than rock.
Less dense.
Right. So we're going to get a larger answer than we would for a rock. That's okay.
And I was gonna try to.
All right. And when we do this now, we see that all the units cancel out, which is very nice. And did you actually get a number for this?
I got 32. I rounded up 32 cubic feet.
Great. Aha. So I guess the question for you was how to relate this to a cube.
Yeah.
No problem. Draw yourself a cube. And when you draw yourself a cube, I was going to be fancy about it, but I won't. Of course, you guys all learned how to do this. Then, how can I mark up the sides for that cube? Any suggestions?
Each side would be cube 3 to 32.
Yeah, well, yeah, that's right. That's where I was headed with this. But when I say mark up, I just mean to label them. So each side would be S, right? And now we're going to correspond this with this by asking, what's the volume of our cube? Why, that would be S cubed. And what's the volume of our cube? Why, that would be 32 cubic feet. And therefore, S would be the cube root of 32. Let's see here. Off the top of my head, the cube root of 32, that's kind of tough. I know that 2 cubed is 8. I know that 3 cubed is 27. We're getting pretty close. And 4 cubed is 64. So this is going to be 2 point something. The calculator will tell me exactly what. But I'm going to call it approximately 2, because that's pretty close feet on each side. And for rock, what changes? This was our density for water that I guess they gave us in the problem. What would change if I used rock? Does the density go up or down? Definitely up, right? Because rocks do not float. And therefore, this number here would be larger, making this volume smaller, making this side smaller. So it turns out that for rock, we might be down as far as 1 foot on each side. That's probably 1.5 is what I would want. This seems, are you sure this is for water? This seems a little high for me. Does it say that?
It says rock has mass per volume about 3 times that of water, which is 1 kilogram per liter, or 62 pounds per cubic foot.
Huh, okay then. Okay. So where does the dividing by 3 happen? Well, the dividing by 3, this number would now become 186. This would then become 1/3 of that, or 10 cubic feet. And so we would end up taking the cube root of 10 rather than, which is closer to. I said this is about 2. This is, I'm sorry, about 3, right? I'm being stupid. 3 cubed is 27. Here we go. This is for water. And then if we did for rock, then we have 1 ton times 2,000 pounds per ton times 1 foot cubed per 186 pounds. And that comes out to, let's call it 11 cubic feet. Which is going to give me approximately 2 feet on each side. A little bit larger than 2 feet on each side.
So would you round up to 3? Because they only give you 1 foot 3 for their size of a car.
I think you would actually round down to 2. Oh, are those your only choices?
Yeah, they give you 3 choices.
I think those were supposed to be guiding choices rather than your only choices.
Oh, okay. All right.
Yeah. And that makes about sense. I could picture a 2-foot rock, 2 foot by 2 foot by 2 foot, weighing a ton. Yeah. The 1 wasn't working for me, because I'm pretty sure I could lift it 1
Yeah.
by 1 rock. Yeah. Okay. Now, come back to a couple of things about this. One is, I'd like for you to notice the format. I know it's kind of spread over a page here, but if we take a look at the format for solving the problem, notice that we've got the conversion factors, just as I mentioned yesterday. Everybody should have the conversion factors. If your conversion factors don't look like this, you're probably doing it wrong. Joseph's like, oh man. But I did tell you yesterday, right? And I meant it. And then notice here that I've got a diagram that leads to this equation, and my units are in place at all times. Units are a thing. So we're going to have our units in place because my quantities don't make sense without those units. If I just say the side is 3 watts. Good. All right, we have time for one more question. Okay. Number 44 says, a heavy rainstorm dumps a centimeter of rain on a city 5 kilometers wide, 8 kilometers long in a 2-hour period. How many metric tons of water fell on the city? This is one of those questions that is supposed to make you go, wow. Because a centimeter is a little bit under a half an inch, right? So we're really asking the question, how heavy is a half an inch of rain on an entire city? So that's our setup. Now, what did you do with it?
I converted I multiplied the centimeter by, no, I converted the 5 kilometers and 8 kilometers to centimeters, so I could find the volume
Mhm.
to the so I multiplied 5 times 10 to the 5th centimeters by 8 times 10 to the 5th centimeters by 1 centimeter.
Okay. So implied in here is that there are 10 to the 5th centimeters per kilometer. Did you get there in 2 steps?
Well, I just moved like the decimal.
Move the decimal point. Okay. With the metric stuff, with the metric units and converting, eventually you'll get to the point like Tife where you can move the decimal point and that's okay. So eventually I'm not going to expect you to show the conversion factors here, but now, unless you're a real expert at it, I'm going to expect you, if you're making mistakes on them at all, I'm going to give you a nasty note about conversion factors. So you got that, and now you multiplied all of that together. Implied here is a picture, so I would have liked to see a picture first. What are we talking about exactly? What picture should we draw for this rain that we're going to represent?
Like a big 3D rectangle.
A big 3D rectangle that has one dimension that's not like the others.
1 centimeter long.
Right, exactly. So we can't even draw this very well without exaggeration because, there we go. Here's our rectangle. This big 3D rectangle is way too thick. Also, I kind of had to draw it on its side because I didn't have any board to its thing. How can I get that so that it's... Well, anyway, this is way too thick because actually each of these dimensions right here is 8 times 10 to the 5th and 5 times 10 to the 5th. And this is just 1. So we're talking about the thickness.
It has to be like,
Right, the thickness being 1/100,000th of it. So if this is 8 centimeters in real life, and that's about 5, then we're talking about 1 times 10 to the minus 5th centimeters, which would be 10 to the minus 4th millimeters, which would be 0.1 micrometers. And it's hard to draw that. So this is an exaggerated diagram. Notice also here that we're using a simplified model for the rain. Does the rain actually fall in one big rectangle? Of course not. It fits the contour of the land and blah, blah, blah. Nevertheless, that is a good model. Why?
because after the rain stops, where it lays.
Well, but it lays all across the surface of the land. Why is that a good model, though? Yeah.
It shows that we're trying to express volume.
Yeah. It's an easy computation. So this is a simplified model. That gives an easy computation. This is one of the things that scientists look for when people who are not trained scientifically try to solve problems. A lot of times they make the problems too hard. they think about, oh my gosh, I'm gonna have to sit there and like figure out all the different pools in the city and puddles and like add them up and blah blah blah. No. Let's take the rain and spread it out evenly. But there's another thing about our model that is really nice, and that is that rain falls evenly, doesn't it? So if the city happened to be one large square swimming pool, rectangular swimming pool, then the rain would fill up at an even level. The common phrase is water seeks its own level. Have you ever heard that? Right? And that just means that liquids have a tendency to spread out so that they make a level surface anyway. So it turns out that even though the rain is not going to take this shape once it has fallen, nevertheless, this is a very good way to do the drawing. So this is a simplified model, and I want to encourage you problem solvers to seek out simplified models, rectangles, spheres, those kinds of things. The joke among physicists is that a physicist will tell you, assume the horse is a sphere. And that's the simplified model thing at work. Okay, go. Oh, hello. So my volume is 5 times 10 to the 5th centimeters times 8 times 10 to the 5th centimeters times 1 centimeter. And we can do this in our heads. 5 times 8 is 40. 10 to the 5th times 10 to the 5th is 10 to the 10th. And centimeters times centimeters times centimeters is, yeah, or 4 times 10 to the 11th centimeters cubed worth of rain. We are now suitably pressed. Okay? Good.
So they use
Yeah, that's actually correct. The density of water is usually given as 1,000 kilograms per meter cubed, and if you work out the conversion factor, it goes to that. It's also given as 1 gram per centimeter cubed, which is how chemistry students remember it. And 1 gram is 10 to the minus 3 kilograms. So that's great. And so we multiply this together, add the exponents, and we get 4 times 10 to the 8th kilograms.
I multiplied it by 1 metric ton over 10 to the 3rd kilogram.
Okay. Good. So everything seems hunky-dory with this problem.
I didn't know if I was doing it right last
Oh,
time.
you're absolutely doing it right. This is going to be this is going to be the mass of that water in metric tons. And if you were intimidated by how big it was, you're actually supposed to be impressed by how big it is. Now we understand why floods are so destructive. Because of the mass of that water coming through is humongous. This is 1 centimeter's worth of rain. Now imagine if you get 5 or 6 inches of rain in an hour, and all that water has to go somewhere. Multiply this, 5 or 6 inches would be 10, 12 times this. And if all that rain funnels, let's say, down into a narrow canyon or something like that, the people at the bottom of that canyon are going to have a real bad time. Okay, that's great. What's the relationship between a metric ton and an English ton? Well, 1 kilogram weighs 2.2 pounds on Earth. So 1,000 kilograms, a metric ton, is going to be 2,200 pounds, or a little bit more than an English ton. So a metric ton is slightly larger than an English ton by 10%. Good. All right. Well, that takes care of our questions. Again, if you have questions on homework, Edmodo is the place to go. And the way I'm going to do things is you put up a question, That will allow me to look ahead of time and say, okay, I need to address this in class, or another person to say, I don't know how to do this, blah, 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 blah. And, or, I don't know how to do this, but here's what I did. And then, hey, that's probably right, which is where Tipe was. Good job, guys. Let's talk density.
Do you want us to turn it on?
Yes, I'll take homework. For those of you who are playing at home, you may attach a picture of your homework to Edmodo, or you can email it to me. I want to start off with a picture of matter. Imagine just a cube here, and the cube doesn't have to have any physical sides to it. It's just a mathematical cube that I'm drawing somewhere. And now we're going to capture all of the matter that is found in that cube. Question for you. As you've learned in chemistry since the 1800s, we believe that all matter on Earth is made up of atoms, and those atoms in turn are made up of protons, neutrons, and electrons, as my daughters have gotten used to me saying at the dinner table. So that when you're eating yummy ice cream or you're smelling disgusting, rotten, whatever, protons, neutrons, and electrons simply rearranged, which is kind of one. But the next question is, how densely are they packed? And the answer is, it depends upon the type of matter. So if I have a not dense material, such as, what state of matter is not very dense? Gas, that's right. And also plasma, if you've heard of that. Plasma is a gas whose electrons have been separated from the nuclei, or at least the outer electrons. So plasma is ionized gas. Then the picture of matter that we would draw is that there are going to be a few atoms that are going to be widely distributed, and probably in rapid motion, colliding with one another frequently. On the other hand, if we have other states of matter, liquid and solid, then my atoms are going to be very densely packed. Like so. And we can characterize the packing of these atoms with a mathematical quantity called the density. And in chemistry, you probably use D for density, but physicists use D for distance. So we're going to use the Greek R, which is rho, which looks like a P, but is not. I don't actually know the history of why rho is used for density.
R-O?
R-H-O. Is what you would spell it. Rho. What's the joke? Yeah. Yep. Anyway, back to our story here. My aim in life is to make my daughters roll their eyes. Yep. It's a dad thing.
Dad jokes.
Dad jokes. Okay. So density is defined as mass over volume. Now here's what this means. This means that we are going to measure how much stuff we have packed in, that's the mass, per unit volume. In other words, if my volume is large, then my density will be small, even if I pack in a fair amount of mass. If my volume is small, then my density will be large even if I packed in a moderate amount of mass. So the distinction between density and mass goes like this. You've probably heard this before. Which is heavier, a pound of lead or a pound of feathers?
Looks like it's because you have to carry the guilt of the birds you killed.
Yeah. But the answer is they weigh the same because they both weigh a pound. But now the question is which is larger, occupies more volume, a pound of lead or a pound of feathers? And the feathers, clearly, because the feathers are less dense. How big would a pound of feathers be? Probably about this, right? How big would a pound of lead be?
Yeah.
Right there.
Yeah.
And the difference between the two is that the lead is much, much more dense than the feathers. Lead has a density of 11,200 kilograms per cubic meter. Dang, you don't need to write that number down. But we'll get some numbers here. So let's actually go through and characterize some different states of matter. And I want to give you perspective on this, but there are only a couple, there's only really one number that I'm going to ask you to remember. If we look at gases, their densities are going to be very, very small. They're going to be on the order of 2 to 3 kilograms per cubic meter. 1 to 3 kilograms per cubic meter on at 1 atmosphere of pressure. Now we have to specify that because gases, because there's so much empty space between the molecules, gases are subject to compression. So if I compress that gas, then I can make the density go up. Solids and liquids are going to be hard to compress. You can do it, but you have to put a lot of pressure on them. As we go to liquids, most liquids are going to have, densities somewhere in the range of about 500 to 3,000 kilograms per meter cubed, but there are exceptions. What's the most dense liquid that you know? Mercury, that's exactly right. Mercury has a density of 13,000 kilograms per cubic meter. If you were to jump into a large pool of mercury, in addition to possibly poisoning yourself, you would find it difficult to swim because you wouldn't be able to break the surface very well.
You're okay with your lungs being compressed?
If you were beneath it, yeah, your lungs would be compressed. That's right. You have a lot of weight of mercury coming down. And then you go pop like a ball. Not pop, but pop like that. Sort of like when you take a ball and put it underneath the swimming pool, right? And it goes pop. That usually is.
Okay. You like hold the ball in there.
Yeah, you hold the ball under. Solids. Solids are going to have densities anywhere between 10 and maybe 20,000 kilograms per cubic meter. What's the most dense solid that you know? Uranium is pretty dense. Yeah, that's right. Gold even a little more so. So those movies where you see, like, anybody watch The Italian Job?
Yes.
Yes, where they pile the gold into the back of the car. Not happening.
Not happening. Because that was a lot of gold.
It was a lot of gold. That's right.
Or even for a souped up Mini Cooper.
If we just think that we said that a rock that is 2 by 2 by 2 is going to be about a ton, right? So the gold is going to be about 4 times as dense as that. So take that down to like, well, a cube root 4. Yeah. So you're going to have multiple tons, and that poor little Mini Cooper is just going to be toast.
It would have been hanging.
How might we get denser states of matter than well, not denser states of matter, but where might we find denser matter than even this?
Jupiter.
Jupiter, why? What's going on there with Jupiter?
Gravity is fine.
Yes, gravity is compressing that so that we get even denser than on Earth. And so if we take a look at the core of the Earth is about 12,800 kilograms per cubic meter. The core of Jupiter is 70,000 kilograms per cubic meter. And if we go to the core of the Sun, it's about 150,000 kilograms per cubic meter. Now, I said there was one number I wanted you to know, and that's a reference point, and here it is. On Earth, at 1 atmosphere of pressure at 25 degrees Celsius, in other words, under normal conditions, water has a density of exactly 1,000 kilograms per cubic meter. I guess the specified condition is at 4 degrees Celsius. Yes.
The density of solids is it one? You said 10,000.
No, 150,000. Did I say 10?
Yeah.
I meant
No, you wrote 1,000 solids.
I'm so confused.
When you said 10,000.
Yeah. Uh-huh.
You
Yeah.
said 10,000, but you wrote 1,000. So is it 10,000?
Oh, I meant 1,000.
Oh.
Yes, this is correct. You're going to have solids that can float on top of water, right?
Yeah.
And so water here is our reference, just so you can kind of get your bearings. If you think of everything in terms of water, then Sun is 150 times as dense as water is. The core of the Sun is 150 times as dense as water, which is great. What might be denser than that? Dark matter, we don't know a lot about dark matter, so maybe not.
A black hole.
Black hole, right? That'd be the extreme, right? And in between there, you would have what are called neutron stars. Neutron stars are stars that are made only of neutrons, and therefore there's no repulsive force they can get in there. They're about 1.5 to 5 times the density of the Sun. So that's going to give you up to 750,000 kilograms per cubic meter. But now something crazy happens, and that is this. That if you get more dense than this, then the gravity that is created by that dense matter begins to pull the matter in even further. And as a result, there is a runaway gravity well that is created, which we call a black hole. Measuring the density of a black hole is kind of a tricky question. I looked around on Physics Stack Exchange for some answers to how dense is a black hole, and it turned out that physicists kind of have difficulty with that. But here's probably the best way to do it. Around the black hole, we can draw a small circle called the Schwarzschild radius that is the boundary past which light cannot escape. And if we take that to be the radius of the black hole, and then we divide mass by volume, then we're going to find that the black hole's density is approximately 10 to the 16th kilograms per cubic meter. In other words, we go along, we're getting steadily more and more dense, and then poof, we blow out at 10 to the 16th kilograms per cubic meter. Or in other words, about 1 trillion times as dense as the Sun. No, I have that wrong. Do I have that wrong? I had that point, about 1/10 of a trillion times as dense as the Sun. Okay, there you go. Well, this was kind of entertaining, but the real question is, how do you use this density here? So we're going to do a couple of things. First of all, we're going to compute densities. And for that, I'd like to just ask a simple question. What is the density of the moon? Is the average density of the moon? Well, let's see. We need to know some numbers. We would need to know the mass of the moon, and we would need to know the volume of the moon, right? In order to compute it. Well, I don't know the volume of the moon, but I do know the radius of the moon. What simple model could we use for the moon in order to compute its volume? The moon is based, pretend the moon is a sphere, which is pretty close. By the way, one of the characteristics that's required of a planet to be a planet is that it be spheroid in shape. Which means a lot of those asteroids would not qualify no matter what.
So what if there was a square planet?
Then a lot of physics would get overturned. It's a good question. Okay, so we have the mass of the moon is 7.35 times 10 to the 22nd kilograms. And we're going to have the radius of the moon as 1.74 times 10 to the third kilometers. Now already we've got a slight issue, and that is that we probably don't want our density in kilograms per kilometer cubed. So let's go ahead and convert that dimension into meters, giving me 1.74 times 10 to the 6th meters. For reference, the radius of the Earth is 6 times 10 to the 6th. So the moon is about 1/3 the diameter of the Earth. And now we're going to use a simple model of a sphere. We want to draw that model so that it's clear to our reader what's going on here. And we're going to need to compute the volume. What's the volume of a sphere? Some formula.
4 times pi to the r cubed.
That's it. 4/3 pi r cubed. Very good. If you didn't know that, to the BATnet. You could find it right there on Google. And so that gives us this. Okay, everybody compute that. Go, go, go. I'll pause the tape here while you compute at home. And so we get a volume here of 2.2 times 10 to the 19th cubic meters. And now the game is won. We're looking for the density, and so we write our formula. Let me strongly encourage you to write your formula before you go plugging in numbers. I have a lot of students that will skip this step, and it is a false savings. It only takes a second to write down your formula, and it saves you a whole lot of grief. So we're going to adopt that as our format of formula first, and then plug in values. For our mass, we have given 7.35 times 10 to the 22nd kilograms divided by the computed volume, 2.2 times 10 to the 19th meters cubed. Now our calculator is going to tell us what the answer is, but before we get there, let's estimate it. 7.35 divided by 2 should be about what number? 7 divided by 2? 3.5. So we should get about 3.5 times 10 to the 22 divided by 10 to the 19th. Subtract the exponents and get. Yep. So I expect that I should get about 3,500 when I actually compute it. Predicting what your calculator tells you is a skill that every scientist should develop. Predicting what your calculator should say is a skill that you should develop because, again, everybody does fumble-fingered stuff on the calculator, and you want to have a good sense of what your answer should be. So if that estimating skill is challenging for you, then the way to get better at it is to practice, practice, practice. To make a prediction, and then if you're wrong, come back and say, why was I wrong? And if you're right, you can say, hey, I'm doing it right. Oh, look, what do you get for the density? Now let's check our sig figs here. Looks like we want, You know, my original had 3 sig figs in the radius, so I probably should have reported out 3. This should be 2.21 here, and so what do we have? It's 3.326. There we go. So we're going to clean up our answer by rounding it to 3 sig figs and making sure that it has the right units. And that's how the computation is done. The second thing that we can do with density is to use it to predict mass or volume. So, for example, I might ask the question, let's see here. I might ask the question, what's the total mass of water in a swimming pool? Have you ever wondered that? Like, how heavy is all the water in a swimming pool? We can do this fairly quickly because we only have 1 minute. What simple model should I use for a swimming pool? No, not a rectangular box, absolutely. If we want to make it Olympic, do you know the dimensions on that?
50 by 20. 50 meters by 20 meters.
By how deep?
It varies, but
don't think-
typically it's around 13 at its deepest.
13 feet, right?
What, it's just,
Yeah, so 13 feet would be 4 meters. Let's take an average depth of 2 meters. So we're going to pretend that the pool is a box. It isn't really. It's really one of those trapezoidal weirder shapes like that. And I would need calculus to compute the real volume. Let me finish this because it's going to be real short. We have 50 times 20 times 2 is going to be 10 times 2 is 20 with 2 zeros. Gives me 2,000 cubic meters. And the density of water is known as 1,000 kilograms per cubic meter. Notice that I'm using density as a conversion factor. I don't have to plug it into the formula because it's a proportional thing. And so that gives me 2 times 10 to the 6th kilograms, or about 2,000 metric tons of water. No wonder it hurts to go all the way to the bottom. See you later.